This will be the volume of pyramids and cones. Let's start with a thought back to when we were doing triangles. We recall that whenever you have a triangle, it's possible to place it into the smallest rectangle that you can, and that once you do that, the triangle is half of the area of the rectangle. Okay, again, a rectangle, the triangle that just fits in it is half of it. Let's see what happens when we take three-dimensional shape. So here we've got a prism, a rectangular prism, and a pyramid. They are the same dimensions. They have the same base, it's a square, and they are the same height. So, their measurements are the same. The base is the same, the height is the same. I wonder what's going to happen if I put it in there. I wonder how much that'll be. Okay, I have a three-dimensional shape. I'm going to project it and create a two-dimensional shape of it. It's kind of flatten it down. I hope you can see here that what we see when I take the three-dimensional shape and by the use of this screen make it flat, it's flat on your screen, that it now looks like a triangle and a rectangle, the one that we just saw. A triangle inside of a rectangle. Well, we saw that the triangle was half of the rectangle that just barely enclosed it. I wonder if that's a relationship between the pyramid and the prism that just barely encloses it. They have the same dimensions again. Well, let's see what happens. I'm going to take some handy dandy parakeet seed. My parakeet died. Poor thing. So I got some parakeet seed, and I'm going to fill up the pyramid to see how much of it it'll take to fill the prism. Okay, there's one pyramid full of birdseed, and I'm going to pour it into the prism. So there's one. I wonder if it's half. Oh my, I don't think that's half. What do you think? I don't think it's half. Try it again. Okay, I'll fill it up again. Fill up my pyramid. How many pyramids will it take to fill my prism? There we goes two. Oh, that didn't do it, did it? Looks like about, I'm wondering if it'll be three. Let's try it and see. Okay, I'll fill the pyramid again. It's a little bit short, so I need just a little bit more. I'll take that to fill up the space. So what do I have? I have, it takes three pyramids to fill a prism. Who'd have thought? Three pyramids, and this is a three-dimensional figure, and three pyramids fill one prism. Pretty good. In the two dimensions, in the two-dimensional shape, it took true triangles to fill, it took two triangles to fill a rectangle. I'm pouring this back in here. Here it took three pyramids to fill one prism. I'm going to go ahead and put this so that you can see it. Maybe if I turn it around, it's actually, obviously, since it's on your screen there, you're not seeing in three dimensions. But maybe you'll be able to get an idea that there really is a lot of space So since it takes 3 to fill it, there really ought to be twice as much space. Now when you're looking at it like that, it looks like the triangle in the prism, a triangle in the square, and it looks like half. But I'll kind of rotate it around. As I rotate it around, hopefully you can see that there really is more space that doesn't have birdseed in it than there is space that has birdseed in it. If you think about it a little bit, kind of cut it this way and turn it that way, you can see that it's reasonable that there's twice as much space without birdseed as there is space with birdseed. And there is. It turns out that exactly 3 times the volume of the pyramid is the volume of the prism. So recall that prisms are really easy to do. They're just length times width times height. Just slice it a bit and you're done. So the easiest way to do the pyramid is to just say that it's half of a prism. Well, these are all straight, flat sides. I wonder what happens if I have a curved side. Here's a cone and a cylinder. What happens if I put the cone into the cylinder? Remember again, here is the triangle and the rectangle. But surprisingly, perhaps, even though this has curved sides, when you do the flat projection, it still is just half of, half, and it's a triangle in a rectangle. If I put some birdseed in that, you can see it a little bit better, maybe. So the flat projection of it again. If I can get it. Is it still looks like a triangle inside of a rectangle. It didn't matter that it had curved sides. And if you look at it, as I turn it around, hopefully you can see that there's more space than there is birdseed in the cylinder. It's actually twice as much space as the one birdseed. Okay. So we have then that the volume of a pyramid and the volume of a cone is a third of the volume of the cylinder or the pyramid. The cylinder or the prism. Let's get a generalization here. In two dimensions, you have two shapes with the same dimensions. In 2 dimensions, the same measurements, or dimensions, the same measurements. The triangle barely fits into the rectangle. The base is the same length. The height is the same. Base is the same length. Height is the same for the rectangle and for the triangle. It's got a pointy top. It's got straight sides. 2 pointy tops fit in one straight side. 2 pointy tops fit in one straight side. A piece over here, makes the same thing like we did before. 2 pointy tops fit in one straight side. Well, how does that work? With the 3D. Okay, these have the same measurements. The base area is the same. The dimensions of the base is the same. They are the same height. They have the same dimensions. So given that they have the same dimensions, we've got straight sides on the prism. We've got pointy top on the pyramid, and 3 pointy tops are going to fit into the straight side. 3 pointy tops in the straight side in 3-dimensional figures. 3-dimensional figures, pointy top, 3 pointy tops going to fit into straight side. Same for the cone. The cone is going to be, even though it's a curved space, it'll be a pointy top and a straight side. Here's the pointy top. Here's the straight side, pointy top, straight side. 3 pointy tops are going to fit into the straight side. It works for all of them in 3 dimensions. In 2 dimensions, it's 2 pointy tops for the straight side, fit into the straight side, which is a triangle and a rectangle. Here we have some composites. How are you going to figure these? Okay. Figure them up and add them, and some of the ones you're going to subtract. This is a cylinder. The radius of the base is 3 centimeters. The height is 7. So this is pi r squared h, or capital B, area of the base, times height, pi r squared h. So that'll be pi times 3 squared times 7. That'll give you the volume of the cylinder. To get the cone above it, it has the same base, so it's pi r squared h divided by 3, or 1/3 pi r squared h. It'll be the calculation, pi r squared, so that's pi times 3 squared, pi times 9, times the height 3, and then divided by 3. Calculate them separately and add them together. Here we have a cube, 10 by 10 by 10, with a hole in the cube that is the shape of a square pyramid. We know it's square because we can see that the marks here at the corners indicate that the side lengths are the same. Since these 2 side lengths are the same as all the rest of them, this is isosceles, and it is split in half. The edge is split in half, so this is 5 and 5. So from your special right triangles, this distance is 5 times the square root of 2. The square is 5 times the square root of 2 times 5 times the square root of 2. That's the base of the pyramid. So 5 times the square root of 2 times 5 times the square root of 2 is 25 times 2, which is 50, times the height, which is 10. Figure the volume of the entire cube, subtract the volume of the pyramid. There are a few more here to do. This will be 2 cones. Notice that they're not the same cone. If they were the same cone, it would just be 1/3 of the whole cylinder. Here's a 1, 2, 3, 4, 6, an octagonal pyramid inside of a cylinder. That's a hole again. So you'll find the cylinder and subtract the octagonal pyramid. And here ended the lesson.